Morning, everyone. Today's lesson is on section 6.3. As you can see by my sheet here, it's called Conditional Probability today. So we're going to add what's called the multiplication rule today and how to deal with other types of probability. So what I have here is a little chart. It's right out of the book, actually. It's actually some data on the Titanic. And what you see is what's called a 2x2 chart. The reason it's called a 2x2, it looks like it might be a 3x3 chart, is because really all of the information that we need is in those four things. The totals would typically not be in a chart. They're just there to help us save us time because we're going to need those totals in just a second. So it's a 2x2 or a two-way table. What you see here on the top is the gender. So there were 1,731 males, 470 females on the ship. And then the other piece of data is whether or not they survived, right? So conditional probability, first of all, we could answer questions like we just did yesterday. I could say, what's the probability? A quick review, actually, a good idea, I guess, is, let me do a little bit of erasing here. Probability, if I do like yesterday, what's the probability of being male or survived? You would do the males, which are the 1731, or survived, which are these people, which is 711. But then we want to subtract the overlap again. There's that overlap, right? That 367. So we're going to subtract the 367, all out of the total amount of people on the ship, which is 2201. I'm going to leave the computations for you. But that's kind of a quick reminder of what we can do from yesterday, or the last lesson. So now, give me a second here. All right, so now we're going to do what's called conditional probability. So a little notation for you. This is the notation. Actually, this line should be, I guess we didn't get that in there right, should be a vertical line. So probability of A vertical line B, when you say that, means what's the probability that A happens given that B has already happened. Okay, so what's the probability that A happens given that B has already happened? So there's some precondition that has to be met first, all right? So I got a bunch of questions for you. We're going to go through now. There's going to be the formula for this that I'll walk you through in a second. But I think I got like 6 different problems here I'll kind of walk through with you. Just kind of give you an example. I'm going to leave them in fraction form. The first question is just what's the probability of females? So just make sure you can read the chart. So I look up here at the females. There are 470 females. So that's 470 out of 2201. And again, you wouldn't really leave your answer like that. You'd write it as a percent. This now says what's the probability of survived given female. So now this is a conditional probability. This is the new one, survived given female. So we are only considering those ones who did that backwards. We're only considering the ones who are female. So the precondition that has to be met is that they're female. So it's probably they survive. So we're only talking about 470 people right now. It's not out of 2201. So this one, by definition, is just going to be out of 470. And then it's what's the probability that they survive. These are the survives. So it's 344 out of 470. So if we're looking at a chart and there's a preconceived thing that has to happen, or a condition, the condition that has to be met first, it's either going to be one of the rows or one of the columns. So give me a second. I'll get that out of there. And that will go. Next one, probability of female given survive. So this time we're only looking at the people who survive, which is that row, 711. And the probability they're female would be the 344. And again, write that as a percent. All right. I put this not in here just to talk about notation also. So there's another notation. It's called not A is called the complement of A. And we write it usually called A bar. Okay. And the probability of that is just 1 minus the probability of A, right? Because either A happened or it didn't happen. And clearly, if I go to this problem, not female is male. I mean, you know that, right? So at least in the condition of this problem. not female, but you could just go to the females, which are 470 out of 2201, and subtract that from 1. Or you could just look at the males, just kind of giving you a little different. So I'm going to actually stop here, save you some time. They're all kind of the same, except for this last question. Hopefully that helped a little bit with conditional probability. This last question says, find the probability of female and survived. So that's a little different place to look. Female and survived, as we go right up into this little, there are the females right there that survived. So this is 344 out of 2201. Okay. The reason I did that problem is a little different. It's pretty straightforward, pretty easy. Just go to one box in the chart. But we're going to try to generate a formula for that. So a lot of times in math, especially higher level math like we're in, I like to generate formulas instead of just telling you how they work. So what I'm going to go through here is pretty quick. Let me do a little this first here. Just we're going to hide that on you a little bit. And we're going to hide that on you a little bit. This is just a tree diagram. I know it's hard to follow along with both. If you happen to have your book, you can go back to the numbers in the chart, and I'll kind of flip back and forth. I'm not going to go through this fast because it's just a generation of a formula. I could probably just give you the formula. But I want to try to show you something a little bit where it works. So what you see is a tree diagram that has the two conditions, gender and survival. So gender, what you see right here is the females. Whoops, let's make that a little thinner there. Are the females, which are 470 out of 2201, and the males, which is the 1731 out of 201. And then we have the conditional probability. So here, right, the next one is what's the probability to survive given female? So we go to that 344 or 470. Not survive given female are the leftovers, of course, the 126. And then same thing down at the bottom. And then what you have over here are the conditions. So if I said, what's the probability of female and survived? Notice the 344 out of the 2201, okay, is this one. So now we're going to look kind of a little mathematically. Where does this number, because we know the answer to this needs to be 344, over 2201. Where did those numbers come from in this tree diagram, right? So I go back and erase this. Notice that the 470 over 2201 times the 344 over 470, if you multiply those two numbers together, the two numbers that you see in my chart, you get that 344 over 2201. Hence, we have a formula, right? So the formula for the probability of, in this case, female and survive, we'll call it A and B in just a second, we'll make it a formula, is you take that 470 over 2201, which is the probability of being female, and you multiply it by the probability of surviving given that you're female. So that's kind of a formula. Now, granted, if we're in a box or a chart, you don't need this formula. Just go look at that chart and find that 344 over 2201. But if you're just given these numbers in context, that formula is going to do it. So we'll formalize this formula for you into what's called the multiplication rule. So the multiplication rule is the probability of A and B is equal to the probability of A times the probability of B given A. Or you can switch them around. No one's going to tell you which one's A, which one's B, which one's the first one, which one's the second one. Okay. So now what we do is we take this formula and we rewrite it, a little algebra, to get a formula for conditional probability, right? So if I go back to this formula right up here and just take this and divide it underneath, little algebra, we get the formula for conditional probability, that the formula for probability of A given B is equal to the probability of A and B divided by the probability of B. Now it's really important which one's which. B is the one that's the given condition, needs to be down there in the bottom. Again, if you have a chart, you don't need any of these formulas. You can just look at the chart. However, you don't always have that chart. Okay, that chart was just for our purposes in this problem. A lot of times we just get the information and we get little formulas that we have to apply. So this formula is on the note sheet that I gave you the first day. Hopefully I gave you the first day. I'm taping this early. So we can actually try to apply this formula to an older problem, right? The probability of sum of 8 given doubles. Granted, we could just count. I'll show you how to do that in a second. But if I just use this formula right up here, right, probability of sum of 8 given doubles is going to be equal to the probability of 8 and doubles divided by the probability of doubles, right? So you can just apply this formula if you wanted to. The probability of 8 and doubles, I believe, is just 1, right? There's only 1 8 and doubles. It's the 4 out of all 36 outcomes when rolling the dice. And then we divide that by the probability of doubles, which is 6 out of 36. You do some reducing, and you get 1/6. The other way you can think about the chart, it's a conditional probability. 1, 2, 3, 4, 5, 6. I'll write this quickly, sorry. The conditional probability says they have to be doubles, right? So we go back to what we did earlier. Doubles are 1, 2, 3, 4, 5, 6. Those are the only ones we're considering. We don't care about the other ones because that's the condition. And the probability of 8 is that one right there. That's 4 out of 4, 4 and 4, right? So it's just, again, the 1 out of 6. A couple different ways to look at that. All right. So that's a little bit about conditional probability and a formula. Hopefully that helps. The most common place that this conditional probability comes up in is medical tests. And if you've read the paper at all over the summer and all the stuff with the COVID-19 and the testing results and this and that, you might have heard these words, actually, depending on what you're reading: sensitivity and specificity. So here is a little example. Basically, the idea is here we have 10,000 people that we got together to test this test. In essence, does it work? And we know some things that happen. So basically what happened here is the test result. So this side here, we knew whether they had the disease or not before we started this testing. Okay, so we knew that 10 of the 10,000 had the disease. There's the 10. And we knew that 9,990 didn't. Then we gave them the test, and then these were positive results and negative results here. So 59 people out of the 10,000 tested positive, and 9941 tested negative. So now the question is this test any good? So you've probably seen this with the COVID-19. Hey, it has a sensitivity of 50% or a specificity. You might have seen these words, maybe not. And there are some like conditions for, I don't want to go through all of like what's a good test and what's a bad test, but these words are pretty important. So when you're testing the ability to see if you can get the right information, right? No false positive, false negatives. You probably heard those terms a lot also. There's 4 different things you can look at. First one is what's called the false positive rate. And that's the probability of no disease given that you tested positive, right? So we tested positive, but we didn't really have the disease. So if you go up to the top, remember the condition is test positive. So how many people tested positive was 59. And how many of those did not have the disease, which was 50, right? So no disease, 50 out of the 59. That's called the false positive rate. Okay, you tend to get a lot of false positives just because most people don't have the disease is the idea. And then we have the probability of disease giving test negative. So test negative, there's 9,941 that tested negative. How many of those had the disease was just one of those. This is called the false negative rate. Okay. Again, typically not as many of those just because most of the people don't have it. Okay. And then the 2 that mathematicians tend to look at more are actually what's called sensitivity and specificity. So sensitivity is like the correct result, right? So notice the false positive, false negative are bad results. The test positive given you have the disease is what should happen, and the test negative given you don't have the disease is what should happen. So these are the good results. These are typically the ones that mathematicians look at more. So test positive given that you have the disease. So how many had the disease? Only 10 people. And how many tested positive? 9 of those. So we go with 90% for the sensitivity. And then the test negative given no disease was 9,990. And tested negative was 9,940. I'll do that little math in my calculator just so you can see the number, 9,940. That's 99%. So these are the numbers that typically are looked at a little bit more than the bad ones. It's like, how good are we doing on this test? So that's it for conditional probability, section 6.3. Please let me know if you have any questions.